Hello and welcome to the incomplete unofficial course for geometry. I'm Jonathan Tordilla and I won't be speaking this fast the whole time, but I'm just going to give you a little overview of what we're going to go over today. So, it's basically a basic course. It's everything that I learned in geometry, and my school was a little weird, so we didn't cover all the topics that schools usually cover with geometry, but we did cover some other things. What I do not cover in this course is usually relearned in Algebra 2 and in Trigonometry, or later in higher math, like proofs. I will be covering some kind of proofs in a different video, so stay tuned for that. So here's some topics that are not covered, as I said earlier. Proofs, solving triangles with trigonometry, like with law of cosines, law of sines. Some geometry classes go over this, but I do not think it's needed because you usually forget it by the time you learn in Algebra 2. Conics are also not learned. Some classes learn how to, like the equations of circles and other geometric representations of functions, but I'll not be covering that. And also inscribed shapes. There are links down below if you want to learn all this kind of stuff. Inscribed shapes are covered on the AMC 10, and other kinds of things are also on the AMC 10 that you learn in geometry. Also, SAT prep is also available in the links, textbooks, and some resources like Khan Academy. So let's get started. I'll be using this calculator throughout the lesson, so that's just a pointer. So now let's cover some basic topics that you probably remember. What is a point? Well, if you draw like a Cartesian coordinates here, they're rectangular coordinates. There's an x-axis, there's a y-axis, and points, this is how you plot points if you don't remember. To the right is positive, up is positive, and if you want to plot a point, let's say 2, 1, this point 2, 1, that means you go to the right 2 and up 1. If you want to plot a point 3, 2, you go to the right 3, 1, 2, 3, and up 2, 1, 2, that's 3, 2. So yeah, that's how you plot points. So that's what a point is. It's literally a point in space. And what is a line? Well, a line, I'm going to connect these 2 points, and that's going to make a line. And a line continues on forever, like that. So those arrows mean that they're going on forever in that direction, on forever in that direction. If they don't continue, if they just end at a specific point, then it's called a line segment. Now, what are planes? Well, I'm going to draw a little 3D kind of representation. And you can also look this up online if this is a little confusing. But what a plane is this one-dimensional surface in 3-dimensional space. So that's what it looks like here. And what it's supposed to be doing right now, it's actually passing through these axes. This is the z-axis, this is the y, and that's the x. As you can see, I took this and I sort of turned that down, and then there's another axis. So this is 3-dimensional right now, and this plane is this one-dimensional surface, I mean 2-dimensional surface, sorry, and things can be inside the plane. So I'm going to put this point inside the plane, and these points are coplanar, if I'm pronouncing that correctly. That means they both lie inside the same plane. And they're also collinear, which means they lie within the same line. So let's move on. So what are angles? Well, if you remember, in a triangle, the angles sum up to 180. So that angle plus that angle plus that angle, you usually write this measure of angle A plus the measure of angle B plus the measure of angle C, that's the angle sign, equals 180. And that's true for all triangles. For like rectangles or squares or whatever, the angles for squares and rectangles, they're quadrilaterals, meaning they have 4 sides, but they all have the same angle measure, and that's 90 degrees, 90 degrees, 90 degrees, 90 degrees, and 90 times 4 is 360 degrees. And for all rectangles and squares, they all have 90 degrees for each of their corners. They're right angles. That's what it means to be 90 degrees. But the thing is, a square is a type of rectangle, but a rectangle is not a square, because a square means they all have the same side lengths. But for rectangle, they all have, a rectangle can have two different pairs of side lengths, like that. And that's showing that they're the same length. The 2 matches up with 2, 1 matches up with 1. So basically, the more angles you add in a polygon, a shape, a closed shape, you know, the more sides you add, the greater the total angle measure will be. So how many are in this? 1, 2, 3, 4, 5. So basically, you just keep adding 180 the more sides you add. So since this is a 5-sided 1, 2, 3, 4, 5 polygon, that means I'm going to add 180 degrees, 540 degrees. So what does it mean to be a supplementary angle? Well, a supplementary angle means that added to a different one, it equals 180. So these are supplementary angles. A plus B, the measure of angle A plus the measure of angle B is 180 degrees. Now, what is complementary? Well, complementary is a bit different, but same kind of principle here. That's 90 degrees. This other side will be 90 degrees in total. But this angle right here that I'm drawing, plus this angle, these are complementary because they sum to 90 degrees. So measure of angle A plus the measure of angle B equals 90 degrees. So those are complementary. So that's the difference between supplementary and complementary. Now, here's something else that you should know. What are parallel lines? Well, parallel lines are simply lines that have the same slope and that never intersect with each other. So if you took my algebra course, you know that parallel lines have the same slope. So let's just say that's y equals 2, and this one is y equals 4. So they lie on the y-axis and they never intersect with each other. So those are parallel lines. What are perpendicular lines or orthogonal lines? Well, those are lines that form right angles with each other. So like that. And they have the inverse reciprocal kind of slope. So let's say if a line has slope 3/2, then the one perpendicular to it would be -2/3. So I think you get the idea. So that's about perpendicular and parallel lines. Now we're going to talk about something else. Vertical angles. Now vertical angles, they're always congruent. So basically if you draw two lines, any two lines, and you see these angles, they're always going to be the same measure. Okay, now let's talk about making triangles. So when is a triangle impossible to make? Well, if I say, okay, so one side of a triangle, one side is 10 units, and the other sides are 3 units and 4 units. Is this triangle possible? Can we make this triangle happen? Well, let's say we have 10, let's say that's 10, and then let's say this is 3, and this is 4. No matter how much we bend these sides, it's never going to make a triangle. They're just going to fold in on the base. And it's not going to work. So basically, a good rule to remember is if this plus this is less than this, then the triangle is just impossible. But let's say it has 10 units and the sides are 6 and 7. Well, if you take this 10 and then let's say this is about 6, this is about 6, this is about 7. Well, that's going to make a triangle. These are going to meet at a specific angle and a triangle will form. So 6 plus 7 is 13. 13 is greater than 10, so it's going to work. But if it was less than 10, like this, 3 plus 4, it's only 7, and 7 is less than 10, then the triangle is impossible. So that's something good to remember, and let's move on. So now let's talk about area formulas. What's the area of a triangle? It's base times height divided by 2, or 1/2 base times height. what's the area of a square or a rectangle? Well, it's just base times height. And that also applies to parallelograms because they're basically rectangles. Like if you take this part of the triangle and you move it over to here, well, it's going to form a rectangle. So it's just base times height for parallelograms. And if you're like, what's the parallelogram because you forgot? Well, it basically means these are parallel to each other. These lines here, these line segments. That's why it's a parallelogram, because they have parallel sides. So a trapezoid, it looks like this. And what you do with trapezoids is you take the average of the bases, this is base 1, this is base 2, and you divide it by 2. So it's the average of the base. That plus that divided by 2 is the average. And then you multiply that by the height. So yeah, that's a trapezoid. And now rhombus looks like this. Now for rhombuses, their sides, these sides are, they're all the same. All sides are equivalent in length. And to find the area of this, you can either, you could do one of three things. You can form these diagonals and solve the area for this triangle and then multiply it by 4, because there's 4 triangles. So 1/2 base times height of this triangle, and then you multiply that by 4. Or you can simply do something like find the base times height. That'll work. All you gotta do is, here I'll draw another one so you can see. All you gotta do is make this height and then find this length, and it's base times height. Or you can take the diagonals, multiply the diagonals, and divide it by 2. So those are the 3 methods to find the area of a rhombus. So now, that's actually all of our first lesson. Let's move on to the next chapter, where we learn some pretty cool geometry. So the first thing we're going to learn about is rotation. What is rotation? Well, I'm rotating this paper, and I'm rotating this Cartesian coordinate plane, but I'm going to show you how that applies to shapes. So if you rotate a circle, nothing's going to happen because it's just a circle. So it's going to look the same. But if you rotate a square, let's say I rotate this 45 degrees to the left, what's it going to look like? Well, I'm going to draw it on a different part of the paper, but it's going to look like this. 45 degrees to the left. And usually when you're rotating to the left, or rather counterclockwise, you are rotating in the positive direction. But if you're rotating to the right, it's the negative direction. And you'll see why that makes sense later in math, but there's this thing called the unit circle, and all rotations in this direction are positive, and in this direction it's negative, and it's just convention. I mean, that's just what you're supposed to do. So that's how it works. And that's what a rotation is. So what is a reflection? Well, a reflection, here I'm going to move on to a different section of this paper. A reflection. So, you know how when you look at a mirror, you see like an opposite kind of image? I'm going to draw a triangle here. What's the reflection of this triangle across the y-axis, this line? Well, it's going to be a mirror image, because that's what a reflection is, just a mirror image across a line. And it's going to look like this. That's the reflection across the y-axis. So that's what a reflection is. Now, what's a dilation? A dilation is like scaling something up or down. So making something bigger or smaller, but keeping all of the angles the same and the general shape the same. So let's say I have a little square here. I want to dilate it by a factor of 2. Let's dilate that. All you got to do is multiply the sides by 2 and draw it out. And this will be the center of dilation, which means I'm going to keep this point in the same place. Just going to dilate that. And there we go. That's what it's going to look like. That's the new shape. And that's overshadowing the original. So that's what a dilation is. And symmetry. What is symmetry? Well, we're humans, and we have bilateral symmetry, and that means that we're symmetrical only across one, well, no, we're not perfectly symmetrical, but we're sort of symmetrical across one line. So if we cut someone in half, we're symmetrical, which means we have the same kind of shape on both sides. But you see, like starfish or, let's say, sea anemone, they have radial symmetry. So I'm going to draw a bad sea anemone right now. And if you cut that sea anemone in any place in the center, it's going to be symmetrical. So that's radial symmetry, and that's bilateral symmetry. You'll learn that again in biology. So that's what symmetry is. And congruence. This is probably one of the most important ideas in geometry, because congruence, a lot of proofs rely on congruence, and I won't be covering the actual proofs, but I will be talking about congruence and how you can find congruence. So congruence basically means the same shape and size. So let's say we have a rhombus here, and I'm going to draw another rhombus, and since I'm not the perfect drawer, it's not going to be the exact same shape or size, but I'll try my best. And there we go, that's pretty good, I think. These are congruent because they have the same angle measures, they have the same side lengths, and they're the same shape. Now, some ways to show that triangles are congruent, and I'm just going to write them all out here, are side, side, angle, or angle, side, side. I'll explain what that means in a second. Side, angle, side, angle, angle, side, angle, side, angle, side, 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 and hypotenuse leg. Now, what this means is that, well, I'm not going to talk about this yet. This means that they have a side, an angle, and a side, and you have to read it in order, so side, angle, side. And if the shapes have those things in common, side, angle, and the side, sorry, that's not exactly the same, but you get the idea. If they have the same side, angle, side, side, angle, side, then you know that they're congruent. So congruent is written like this. So they're congruent. Angle, angle, side, which means you see an angle, and then a side. Angle, side, angle. Just draw that out for you here. Angle, side, 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 which means they have the same side lengths. And hypotenuse leg just means that they share a hypotenuse and a leg. So, just moving on from that, what's similar? What does it mean to be similar? Well, similar triangles are basically triangles that have like the same kind of ratios, and they have the same angles, but they're different sizes. So these triangles are somewhat similar, because I'm not perfect at drawing, obviously, but they have the same kind of ratios of side lengths, and they have the same angle measures, because angle measures are preserved with similar triangles. So basically, this is a dilation of that triangle. And it's not just triangles, other shapes can be congruent too. There's just different ways of proving that they are congruent, and of course you can see that really quadrilaterals are made up of triangles, so to prove them congruent, you can prove their triangles congruent. So triangles basically apply to really everything. Any kind of shape you can draw triangles within. So maybe not this shape exactly, but you get the idea. So yeah, basically triangles make up a whole bunch of shapes, and you can prove triangles to be similar with two different ways. Angle, angle, or side, side, side. These are the main ways to prove them similar, but I won't go through the proofs right now. I just want you to have like a basic understanding of similar triangles and similar shapes. So let's cover something that's pretty important. The angle bisector theorem. So what is the angle bisector theorem? Well, basically it states, here I'm just going to draw out this triangle here. And basically I'm going to say these two angles are congruent. So theta and theta, these are congruent. Well, they're equivalent, basically. The same angle measure. And what the theorem states, essentially, is that, here I'm going to draw a different one, so I can give you a numerical example. Basically, this and this has the same ratio as this and that. So, this is not showing that they're equal. I'm sorry if that confused you. It's basically just talking about the ratio. So, I'm going to put letters here so I could represent this geometrically, the way people like it. So, basically, AB over BD is equal to AC over CD. And I'm going to add some numbers here, and you can solve for it if you would like. If you feel motivated, then pause the video. But basically, let's do this together. AB, we don't know that, so I'm going to say X over BD, which is 2.8, is equal to AC, which is 5.8, over CD, which is 3. So solve this algebraically, cross multiply, 3x equals 2.8 times 5.8. You can take out your calculator, times 5.8, 16.24. And divide both sides by 3. X equals 5.413 repeating. And let's check to see if our answer is correct. And it's correct. So that's an example of the angle bisector theorem, and that sound effect you heard was Khan Academy. I was doing an example. So basically, just remember this. And remember this diagram, that is equal to that. So that's a way to remember it, and it's pretty easy once you get the hang of it. So let's move on. Okay, now it's time for my favorite chapter. It's the Introduction to Trigonometry. So basically, what trig is basically just, it's involving triangles and angle measures and everything. And there's just something that you really need to know. It's called Sohcahtoa. And I'm going to explain what that means. Just remember what it is. Sohcahtoa. It's very easy to remember. So that applies to right triangles, and right triangles are triangles with right angles. And there are different types of right triangles, but I'm going to talk about some special right triangles. So there are a few special right triangles here. The first one is the 60, 30, 90 triangle. And the other one is the 45, 45, 90 triangle. And the special thing about these is that for any kind of size of this triangle, the ratios are going to be x, 2x, and x root 3. Meaning that if this is like 5, that's going to be 10, and that's going to be 5 root 3. And now for this is going to be x root 2. So if that's 2 and that's 2, then this will be 2 root 2. So those are the special right triangles that you need to memorize. Now let's talk about Sohcahtoa. So Sohcahtoa means sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Now, what the heck does that mean, you might be asking? And, well, I'm going to show you what that means. And I'm going to get out a different calculator, the graphing calculator, and I'll show you what that means. So, basically, sine, cosine, and tangent, those are all functions. And basically, if you type in a degree measure in that function, it returns a value. And you don't really need to know how it gets that value just yet until trigonometry. But what you do need to know is that what it's doing here is it's taking an input value, I use 35 degrees, and it's looking at that angle, this angle specifically, And it's saying, okay, sine of that angle, 35, equals the opposite over hypotenuse. And what does that mean? Well, you know what the hypotenuse is. It's this side. And the opposite, well, it's this side. So it's the opposite over the hypotenuse. Opposite over hypotenuse. And this fraction right here will be equal to this, what that returns. And it's simple as that. It really is. So here's an example. Sine 35 is equal to 15 over x. Now solve for x. Well, we're going to get on x on this side because we're going to multiply by x, and it's going to be x sine 35 equals 15. Divide by sine 35, you can do that. X equals 15 over sine 35. So x equals, get out your calculator, make sure it's in degree mode. You can change that by typing the mode button and changing it to degree. So 15 divided by sine 35 equals 26.15170,193. So I'm going to round to 3 significant figures. So just remember Sohcahtoa. Sine of theta equals the opposite side over the hypotenuse. Cosine of theta equals the adjacent over the hypotenuse, and tangent of theta equals the opposite over adjacent. Now, let's solve some more problems. Okay, say you have a triangle that looks like this, and we have a side 6, an angle 70, and you want to know this side. So how do you find the side? Well, we're going to see what we have. So we have the opposite side, and we have our angle here. And you want to solve for the adjacent side. So you know your opposite side, you don't know your adjacent side, but you do know your angle. So what involves the opposite and the adjacent? Well, think Sohcahtoa. And that's opposite hypotenuse, so that won't work. That's adjacent hypotenuse. But this is opposite and adjacent, so that's what we're solving for, the adjacent. So let's set it up. Tan of theta, which is 70, equals the opposite over the adjacent. So now let's do some algebra. X tan 70 equals 6. Divide by tan 70 on both sides. So x equals 6 over tan of 70. So take out your calculator here. 6 divided by tan of 70. That gives us 2.18. So x equals 2.18. And let's check our answer. And it's correct. So that's how you solve for a specific side. Now, how do you solve for an angle? And these are fun. So let's see if we can get an example here. So we have a triangle, and side and hypotenuse here. Sorry, that's a kind of a wonky triangle, but you get the idea. 5, 2, and what's this angle? So first, let's flip this triangle around. Let's make it easier to solve. So I want this to be our theta. So let's make it so that's on the left side, like in a typical kind of trigonometry problem. So I'm just going to rotate that triangle this way. And we're going to have our theta here, our 2, and our 5. So that's theta, and that's the adjacent. And that's the, that's the adjacent, that's the hypotenuse. So, as we saw earlier, it's tangent. It's tangent of theta, because we don't know what it is, equals the opposite over adjacent, oa, Sohcahtoa, opposite over adjacent. Oops, opposite over adjacent. So, how do we solve for that theta? Well, we do something called an inverse trig function. So, what we got to do is we got to take the inverse tangent of each side. And that'll just cross out that, so we're left with theta equals tan inverse of 5/2. And all you gotta do is go in your calculator here. I'm gonna focus on the calculator now. And I'm gonna say inverse tan of 5/2. And now we have a degree measure. So 68.19 or 68.2. So 68.20 degrees. And that's our answer. That's what theta is. Okay, so we have one thing to cover before we move on. What are alternate interior angles? Well, if we slice a line through these parallel lines here, the angle formed here and here, those are going to be equivalent. They're going to equal each other. So the measure of angle A is equal to the measure of angle B. So just remember that. So now we're moving on. We're moving on to bigger and better things. So let's say we have a circle here, and we want to find the arc measure. What's the arc measure? Well, the arc measure is basically the measure and angles of this kind of section. And to find that, we just need to find the measure of this angle right here. So a way to do that is if you know like this angle, then you just take 360 minus this theta, and that'll give you this theta. Sorry, that's a little confusing. And that will give you this in degrees. So if we do a problem here, let's say it's this, and this angle equals, let's say, 280 degrees. So what's the measure of this? What's the measure in degrees of this arc? What's the arc measure? Well, you would just say 360 minus 280. That's just 80 degrees. And that'll be the measure of that, and that's the same as this. So if it's written like this, A to C, then you would say, well, this arc measure is equal to 80 degrees. Okay, so before we move on, let's talk about radians versus degrees. So what are radians? Well, radians are a different way of measuring angles, and you'll talk about this in Trigonometry, Algebra 2, but basically what a radian is, here I'm drawing a unit circle right now. And a radian is basically the length around a circle that's equivalent to the length of this radius here. So I'm going to take this radius, I'm going to wrap it around, and that gives you 1 radian. And the amount of radians in a full rotation are 2 pi radians. To convert degrees to radians, I'm going to give you some degree measure, 90 degrees. And you want to make that a radian, so what you do is multiply by pi over 180 so that these kind of cancel out. So you have 1, 2, that equals pi over 2 radians. So if you want to convert back, you say pi over 2 times 180 over pi, so these pi's cancel out. That's just 1 and 1. 180 divided by 2 is 90 degrees. So that's how you find degree and radian measures. So basically, those are radians and degrees. You don't really need to worry about them so much right now. Right now we're going to cover something called arc length. And arc length is pretty cool. And you can just relate this back to your old circle formulas. So the area of a circle is pi r squared. The circumference of a circle is 2 pi r, and the r is the radius. So let's say we have a circle with a radius 3, and I want you to find this arc length. How long is this arc length? And the way you find that, and this theta equals, let's say theta equals 50 degrees. So let's find this arc length. Well, all you gotta do is subtract 50 from 360, so that gives you 310 degrees. And basically the ratio of degrees is 310 over 360, so you can just compute that, 31 divided by 36, and you want to store that in your calculator. So let's store that in our calculator. And let's just remember that for now. And now let's find the circumference. So 2 pi r, what's that? Well, that's 6 pi, because r is 3, so 3 times 2 is 6. So 6 pi, that equals 6 times pi. That's 18.849. Let's store that in our calculator. So store b. So now you want to find this. And you know that the ratio here is some number 0.861. So what I like to do is I like to multiply this by the total circumference, and that'll give us this arc length. And then you want to subtract the total circumference from that to get that. So I like to think about it analytically, and the way I do it is it's kind of similar to how I do Algebra 2 in general. So basically, I'm going to subtract a from 1, and then I'm going to multiply that by that circumference, 6 pi, so it's stored in b, and that'll give us that number. So the arc length, that arc length right there, is 2.618 units. So that's the arc length. And if you don't really understand that, that's okay, because I'm going to sort of talk through it again. So what I did here was I said, okay, so what's the angle of this? Well, it's 50. And what's the ratio of that angle to the entire circle? And then I found that ratio. It's that. So then I'm like, okay, let's solve for the circumference so we can get a bigger part, and then we could solve for the smaller part. So I got the circumference at 6 pi, and then I'm like, okay, let's find that of that, so we can have the ratio of the little to small. So what I did was I took the ratio, and then I subtracted that from the whole circumference, and then I got my little arc length. And that's how you solve it. Just think about it analytically. How much do you need to find of the circle? And you just find this ratio of degrees here, if they give you a degree, and then you solve for the arc length. And the same thing really applies for the area of the sector, which I'm going to talk about now. So what's the area of the sector? Well, I'm going to draw a sector here. And what we're trying to find is the area of the sector. And we're going to find that from an angle measure. So again, theta. And we're going to say theta equals 130 degrees. Okay? So let's find, oh, and right, the radius here is 4. R equals 4. So let's try to find this area. Well, let's find the area of the circle first, because that's always helpful. So it's pi r squared. 4 squared is 16, so 16 pi is our area. And let's just compute that on the calculator here and store that. So 16 pi, that's the total area. Now, what's the fraction, what's the ratio of this to the whole thing? So 130 over 360, 13 divided by 36 is 0.3611. So now let's take that ratio and multiply it by our area, and that'll give us that. So let's multiply that by our area, and there it is. That is the area of the sector. It was a lot simpler this time. So that's how you find the area of a sector. So you just take that ratio, you take that fraction, and you multiply it by the whole thing, by the whole area, and that'll give you your part. So it's pretty simple, and you'll get the hang of it. The reason why I'm teaching this is because it's on the SAT, and it's a very important part of geometry, so it's important that you understand this. So, now that we've covered that, we're almost done with basic geometry, basic high school geometry. And what's left to cover are volume formulas. And volume formulas are pretty self-explanatory. I'm just going to give you the formulas, and you just have to plug them in. And usually they're provided for you on tests, especially if you're in a class where they don't expect as much from you during like final exams. So they'll probably give you a formula sheet, or on the SAT they provide you with the formulas. So the formula for a cube, a 3D cube here, that looks more like a prism, but I'm sorry, it's just side cubed. So side times side times side. The volume for a rectangular prism, it's kind of self-explanatory if you can figure it out, but it's basically just length times width times height. That's the volume. The length times the width times the height. So what's the volume of a sphere? Well, the volume of a sphere, it's pretty simple and easy to remember. Just a little strange. There's a geometric proof of this, but I won't show it to you. It's 4/3 pi r cubed. So that's the volume of a sphere. Now, the volume of a cylinder is pretty interesting, I think. You just find the area of this circle, and you multiply it by the height. So it's pi r squared times the height. And what's the volume of a pyramid? Well, it's pretty easy. The volume of this pyramid here is 1/3 side squared times height. And you could solve for certain parts of these geometric shapes by doing some algebra, by doing some trigonometry, but really it's pretty self-explanatory. And what I mean by that is if you have sort of like an octagon or something, I don't know, I'm just going to draw one, and you have an octagonal prism, and there's like a height that goes up here, and then you have to solve for that. A good way, if you know like this length, is you can like form triangles, and you can solve for this side, and then you can just do all your computations that way, and it's pretty easy. So that's how you apply trigonometry to the rest of geometry. And well, that's basically everything. I covered everything that I learned in geometry when I was taking geometry. And the only thing I didn't cover were like proofs and some really detailed stuff. But basically all of that you can learn on your own, or you can watch some of my other videos. Check the links in the description down below to get more practice on Khan Academy. And thanks for watching, so I'll see you later. Goodbye.